In this video lecture, I will discuss the intuition behind the asymptotic analysis of the factor-augmented regression model. The asymptotic analysis for factor-augmented regression model consists of multiple stages. The first stage is proving consistency. But here we should of course take care that consistency is defined slightly different. We want our factor estimates to be consistent, but not for the factors themselves, because those we actually cannot identify, but for some rotation of the true factors. So here we acknowledge that we don't estimate the true factors directly, but we estimate some rotation, and this rotation of course is the one that makes them satisfy our identification restrictions. So that would be our first step, and if we have that, we can move on then to prove consistency in the factor-augmented regression model. This is what Stock and Watson do in their 2002 papers. Now, if you want to do inference, you need a bit more, because then you actually need that you can treat your FT hats, your estimated factors, as if they were observed regressors. And this is addressed in the paper by Bai and Eng, who proved that indeed, if certain conditions are satisfied, then the limit distribution of the OLS estimator does not change by using the estimates instead of the true rotation of the factors. So let's have a look at the kind of steps we need to prove these results. So if we would know fh, so again, we take a rotation of f, then we could estimate this directly, this model by least squares. And then of course it would be very easy to derive the properties of that model in terms of consistency, in terms of predictions, and in terms of inference on delta. Well, that of course we don't know, so we plug in f hat instead, where we obtain f hat through, for instance, principal components. So what we would need in the first place is to show that f hat converges in probability to f, in which case it follows that delta hat converges in probability to delta. But for inference we need a bit more, because we need to look at not just delta hat conversion to delta, but multiplying it by square root n, and then showing that the limit distribution is the same if we use the true factors or the estimated factors. So we're first going to have a look at the consistency of the factor estimates. Here comes the final crucial assumption of the factor model. So what we need in order to be able to consistently estimate the factors is that the loadings, the loadings matrix is what we call dense. And dense is the opposite of sparse. So where sparse means we have a lot of zeros, dense means we have hardly any zeros. So we have clear non-zeros for most values. So formally, how we define it is basically using taking a squared form. So we take an average of the outer product, lambda j. So on the diagonal, you get for every loading, you get this lambda j squared. And you want, if you average that, then you want these squares to be non-zero. So since we have a matrix here, we're not looking only at the squares. What we want is that the matrix, that it converges to a matrix which is positive definite. And so for this, we need that many of these loadings are non-zero. The reason why we need that is that we need many of our x's to be informative about f. If many loadings are 0, then actually that variable x is not informative about your factor model. In which case it doesn't really help that you add these variables, because you cannot estimate your factor model better anyways. And so this is a very different setup from that we had for the lasso and penalized regression. I mean, there we said yes, p can grow, but we were concerned with how large it could grow, and we did not want it to be too large, and everything should be sparse. So it was really a nuisance. There we really had the high dimensionality, which made life difficult. Here, in a way, we have the high dimensionality, which makes things work. If we only have a few series of x's, we will not be able to estimate the factors. Of course, in the factor-augmented regression model, we would not need to do it then, because we could just estimate the original model. But this is a different way of addressing the high dimensionality. And so some people also say that actually in factor models, rather than the curse of dimensionality, we have the blessing of dimensionality. If we have many series X and they are all informative about the factors, so the loadings are dense, then we can actually estimate the factors more precisely. So let's illustrate this, and in order to make life a bit easier, I'm going to assume we only have one single factor, and instead of using principal components, I'm just going to use simple averaging. In a way, principal components is also averaging. It's also linear combinations. It's just you do weighted averaging, and you do the weights, you select them in an optimal way. So here I'm going to make life a bit easier and just do regular averaging. As we will see, you can also estimate the factors using that. But it will make our expressions a bit easier. So what we're going to do, for every time period, we're going to take the average over all variables j. And that will be our estimate of the factor at that time. So we're going to take the average for j is 1 up to p of xtj. Well, we can write that out. Given the factor structure on x, you can write it out as lambda j ft plus nu tj. Well, then we can already see that ft in this sum does not depend on j. So you can take it out of the sum. So you have ft times the average of the loadings plus the average of the idiosyncratic components. So what we want to recover is ft. That is what we want to estimate. But then of course we need to ensure that this average of the loadings here is not going to converge to 0, because if it would converge to 0, ft would drop out. That would be the case if actually our x's are not informative about the factor. So we need that this lambda is going to converge to a mean which is not equal to 0. This requires that a p goes to infinity and our loadings matrix is dense. Now it also in here actually requires another thing, and that is that the mean itself is also not 0. Well, that is the price we pay for doing simple averaging instead of principal components. Well then, if we can then show that the second term, the average of the idiosyncratic components, goes to 0, well then we are basically have what we need to show. Well, we can prove that the first term converges to a rotation of the factors, but because we only have one factor, a rotation is nothing more than just a multiplication, and that will depend on this, on the value of this of these lambdas here. And the second term converges to 0. Well, this is just showing that an average converges to 0, which means you should do that via applying a law of large numbers to this sample average. Well, when can we apply a law of large numbers? Well, think about the time series case. You can allow for some dependence, but the dependence should not be too strong. So in particular, we need this form of weak dependence, and if that holds, we can apply this law of large numbers to our idiosyncratic error terms. So if we have this weak dependence assumption, we can prove that the sample mean converges to a rotation of the true factor. So here we have again, coming back, this rotation, nu, this mean of the loadings. For that to be non-zero, we need to have many non-zero components, so dense loadings, and we need that the mean is also not 0. So this of course is something that we would not have with principal components, but that we now have on top with doing simple averaging. Now so far we've only been using p p going to infinity. So in fact, to estimate the factors, you only need the cross-sectional dimension to converge to infinity. Where does the n dimension come in? The number of observations. Well, that's when we look at the factor-augmented regression model itself and the delta hat. Now, to manage these two dimensions, there are various ways we can go about. So what we did in the lasso to manage them was essentially make p a function of n and then look at how fast p could increase. So the same you can of course do in factor models, but people in factor models have looked at different kind of asymptotic frameworks as well. So there are some papers which discussed the various ways in which you can let p and n go to infinity, and back then it was important to work this out because people were doing various things before and that could actually lead to very strange results. So Phillips and Moon distinguished three types of asymptotics. They have what we call sequential limits, where you let one, for instance, n go to infinity first, and then you first keep p fixed, and then afterwards, after letting n to infinity, you let p to infinity. You could do a diagonal path limit, where you fix p to be a function of n, but you fix it really to be one single function of n. Or you do the most general thing, which is joint limits, where you let both go to infinity simultaneously, but you may have a restriction on how fast they may increase. And in fact, the last one is what we have been doing for penalized regression. Now, what they notice is that actually with all three you can get different results. So what people actually did before was use sequential limits, because they are easiest to derive, because they look like the most standard case. You let one variable go to infinity, and then you let the other variable go to infinity afterwards. So you both have two more or less standard problems. Suppose you let p go to infinity first and you keep n fixed. Then you can show, as we did before, that your estimates factors consistently estimate your true factors, or at least the rotation of them. But if you would do it the other way around, you fix p and you let n go to infinity, then your estimated regressions are not the same as the true factors, and that will have a consequence on all of the rest of your limits. So depending on which direction you take first, you would get a different outcome. And in fact, if you take diagonal path limits, you also, depending on the diagonal path you take, you might also get a different outcome. And they show several examples of where things lead to different outcomes or not. They also show, on the other hand, under which cases sequential limits lead to the same outcome as joint limits. And as you can guess, joint limits are the ones that we should really be using. They really are the most informative, because they really not only tell you what the limit is, but also under which conditions you actually achieve that limit. So what by and n assume, in terms of joint limits, is that square root n divided by p goes to 0. Note how different this is compared to the rates that we would have for penalized regression. So one way to interpret that is saying p should be at least moderately large compared to n. But if n and p would be approximately equal, then you would say n divided by p goes to some constant, or even goes to 1. That would mean you would have a sample size and n and p which are equal. Well, if that's the case, then obviously this is going to be satisfied, because you have, well, square root n divided by p we can write as n divided by p divided by square root n. So that would definitely go to 0. So you can have n a bit larger still than p, but not too much. And well, this is a bit of a tricky thing, of course, because again, how do you translate such an asymptotic result to a finite sample setting? How can you say, well, this n and p are actually good enough to actually do my factor analysis? So what we can also show is that if square root n divided by p converges to a constant, c not equal to 0, factor estimation is not negligible. And in fact, the distribution of delta hat will change. So that does show that all these distributional results from Bai and Eng are, well, they are quite precise. That there can be cases in practice, of course, where it just does not work that well. Now, thankfully, what we could do, in fact, is use the bootstrap. So without changing anything, but just using the bootstrap, we could actually, in this case, work under this assumption here, as shown in the papers of Gonçalves and Perron. Now let's have a look at what the steps we need to take to prove that the limit distribution does not change. Well, let me start again with the case where we observe the factor. So I'm still working on the one factor. So I'm working with one factor and I have this rotation mu lambda, which is the mean of the loadings. And I'm going to do my factor augmented regression on this factor and my W's. Well, then I can just look at the standard assumptions for the regression model. So I assume that z prime epsilon divided by square root n is going to converge to a normal with some mean 0 and a covariance matrix omega. Now, of course, depending on what assumptions you make, you could make this omega look different. We're not going into that now because it's not crucial for the analysis. You can assume heteroscedasticity and all these things that will not affect the factor model much. Well, same here, we assume a law of large numbers holds for z prime z over n and converges to some sigma z. Well, then that directly follows that the least squares estimator is going to converge to a normal distribution with this sandwich covariance matrix. Again, if you make your life simpler, if you assume I&D error terms, if you assume homoscedasticity, then you can reduce this omega to something like sigma squared times sigma z, which would be like the familiar standard case, and in which case we get the standard limit distribution back. I'm using here the more general form because if you look at Bai and Eng's paper, that is actually what they are using. Now we are going to do the regression with the estimated factor. Now to distinguish the z, the regressive matrix with the estimated factor from the one with the true factor defined here, I'm going to write z hat for the one with the estimated factor. And of course my least squares estimator is just the same as before, but now with the z hats instead of z. Now if I write out my least squares estimator, I plug in for y, I plug in the true data generating process, which is a function of the true z, not of the estimated one. Then normally I would have this term cancelling out. I would get z prime z inverse z prime z, which would be just the identity matrix. And so I would get identity times delta minus identity times delta, and it would cancel out to be 0. Here I don't have that. Here I have this term which looks like it's close to the identity, but it's not equal, minus identity times delta. So I get an additional term here, and also in this final term that I would have before, I have now these estimated set instead of the true ones. So what we need is actually two things. We need that this first term drops out. So that means that square root n times this difference should go to 0. And I need that this second part converges to the version without the hats, with the true sets. So I need that this difference also converges to 0. So what is z hat minus z? Well, it's nothing more than just the estimated factor minus the true factor. So you might think, okay, well, if I have consistency here, this goes to 0. But since we blow up everything by square root n, we need more than just consistency. We need actually a strong form of consistency, which still applies when we multiply by square root n. So p to infinity is actually not enough. Right before we did p to infinity, and then we could show that the sample mean of the idiosyncratic components would go to 0. So now we need more. we need this thing blown up by square root n to still go to 0. And therefore we have restrictions on the relative growth rate of n and p. Now we're not going to go into more details about the asymptotic analysis because it very quickly gets rather complicated. And well, if you want to have a look at how complicated, just have a look at already the first pages of the By&A paper, where life very quickly gets very complicated. So we stop here with the asymptotics and leave it at this intuitive explanation of how the asymptotic analysis works for the factor model. Now what I will do next in the next lecture is I will round up the part on factor models, and I will go back to the part on penalized regression. So we're going to basically look at where we stand now, and what I'm then going to do is I'm going to do an empirical comparison of the two. So I'm going to take a macroeconomic data set and I'm going to do a forecasting analysis there. So I have a high dimensional data set. I'm going to do a forecasting analysis, and with that forecasting analysis have a look at, how does this now work in practice? How do now factor models and penalized regression work in practice? And what can we say about the results? And what can we say about, for instance, what do the factors look like? Which variables do get selected if you do penalized regression, and so on. So that will be the topic of the next lecture.